All right, Professor. So this is the Block 3 video portfolio. I hope you got a grasp of what I learned in Block 1. This one's a little bit more tedious. I really took my time with this one because I really wanted to understand what Block 3 had to offer. It was a lot of things, especially with using L'Hopital's rule. It's very confusing, very confusing just figuring out which, if L'Hopital's rule will be applied to the integrals, and figure out what form of indeterminate to use. So let's jump right into it. So for our first question for relating to improper integrals and L'Hopital's rules, we have limit x to 0 is 9 sine x minus 9x divided by 8x minus 4e to the x plus 4e to the negative x. And we want to find the limit if L'Hopital's rule is applicable. So the first thing we do is determine if the rule is applicable and what indeterminate form to use. So the way that we know if it's applicable is if it's has the indeterminate form of 0 over 0, infinity over 0, infinity over infinity, infinity minus infinity, and I believe 0 over infinity? I'm not too sure. My memory's a little bit foggy, but we know just by looking at this equation that the determinant form for this would be 0 over 0. So to apply the rule, we first determine what indeterminate form to use. Next is to differentiate the numerator and the denominator of the fraction. So we get d over dx times 9 sine x minus 9x equals 9 cosine x minus 9. And then we get d over dx times 8x minus 4ex plus 4e negative x. And that equals 8 minus 4e to the x minus 4e negative x. Now, for our third step, we would obtain the limit. The obtained limit is still in the indeterminate form of 0 over 0. So what we have to do is differentiate once again. So we'll go through 9 cosine x minus 9 equals 9 sine x, and then we'll just bring this down here. d dx equals 8 minus 4e to the x minus 4e negative x equals negative 4ex plus 4e to the negative x. Now, the obtained limit is still in the indiscriminate form 0 over 0, so we have to differentiate once again. And we'll do that once again. Bring this down. 9 sine x, 9 cosine x, d dx, negative 4e to the x plus 4e to the negative x, which will get us negative 4ex minus 4e negative x. So now that we've done this a few times over, let's try and see if we can get the determinant. We can determine the limit using what we got right now. So we'll do limit x to 0, 9 sine x cosine x and for ex. So once we plug in 0 for the x values, we get -9 over -8, which simplifies to 9 over 8. That giving us our limit for limit of x to 0, 9 sine x minus 9x over 8x minus 4 e to the x plus 4 e to the negative x gives us 9 over 8. Okay, so now we're going to dive into improper integrals. So we're going to determine whether the integration of 3 to 6 dt 6 minus t is divergent or convergent. Now, okay. The first thing we want to do is identify the type of given improper integral. So we have a type 1 and type 2. Type 1 is an integral over an unbounded interval. Type 2 is one of which has unbounded range. So we can probably come up with this and conclude that this is a type 2 improper integral. Sorry. So the integrating 1 over dt, or 1 minus 6t, is continuous on 3 to 6 and discontinuous at 6. Now, definition states that type 2, if f is continuous on a to b and discontinuous at b, then the integration of a to b of f of x dx is equal to the limit c that approaches the limit of b from the left from integration of a to c. Is equal to limit of c to b, c that approaches b to the left, integration of a to c f of x dx. We then rewrite the integration as 3b equals dt 6 minus t equals limit c to 6 from the left from 3 to c dt over 6 minus t. So then we now rewrote it, and now we're going to evaluate and answer it in terms of c. So get t, and that will give us negative log sine 6 minus c plus logarithm sine 3, And then now that we have that, we put it in terms of c, we now determine if it's convergent or divergent. So let's go ahead and figure that out. So limit c to 6, approaching 6 from the left, from integration 3 to c, excuse me, dt over 6 minus t equals limit c to 6 from the left times log, and we just plug this in equation log. I'm not gonna, just for the sake of the video and time, I'm just gonna plug in the values. 6 minus t, 6. I messed up somewhere. I meant to say, sorry. Okay, absolute value, 6 minus t. Sorry, I couldn't read my writing. On interval C, 3 to C. Simplify. Let's see. We distribute our limits. We get for this value, for the value here, negative logarithm sign, absolute value 6 minus c, we get infinity, and then distribute logarithm 3. Now, anything plus infinity equals infinity, and that's our final answer. Now, since there isn't a solid limit or value that we have, and we have infinity, the integration of 3 to 6 dt over 6 minus t is divergent. Okay, so now for our last question, we're gonna use the integral test to determine whether the series sigma notation n equals 1, 6n to the 5th power divided by n to the 6th power plus 2 converges or diverges. So before we begin, let's recall the integral test. We assume that an is a decreasing sequence of an with a finite number at where n equals 1 is a decreasing sequence of positive terms, and an equals fn, where f of x is a continuous positive and decreasing function for all x greater than or equal to some natural number n. The series sigma notation with a finite number n equals n times an and the improper integral from a natural number to infinity f of x dx both converge or diverge. So now, since all the terms of this equation are positive, let's check to see if the sequence is decreasing. And in order to do this, we find the derivative of the function f of x equals 6 times x to the 5th power divided by x to the 6 plus 2 using the quotient rule. So we do that. Get the derivative. Now just speed things up. So you simplify version. And we get 6 to the 4th times 10 minus x to the 6 divided by x6 plus 2 squared. Now we determine where the function of x is decreasing. So we find where f prime x, 6 to the x, 6 times x to the 4th times 10 minus 6 to the 6th divided by x to the 6th power plus 2 to the squared is greater than or is less than or equal to 0. This is true for all positive values of x that satisfy the following inequality. So we get 10 minus, so we'll say 10 minus x6 greater than or equal to 0, x6. trying to get my train of thought together. 10. 0.47. So thus f of x is decreasing monotonically for all x greater than or equal to 1.47. And since an equals fn, the sequence an, the finite number n equals 2 is equal to 6n to the 5th divided by n to the 6th plus 2 over a finite infinite number where n equals 2 is almost monotonically decreasing. Now, f of x, 6x, f of x equals, okay, the function f of x, which is equal to 6x to the 5th divided by x to the 6th plus 2, is continuous and positive for all x greater than or equal to 2. So the conditions for applying the integral test are satisfied. So to use the integral test, we evaluate the improper technical integral, the integration sign of 2 to infinity 6 times x to the 5th divided by x plus 2 dx. Okay, now this is where it got kind of tricky for me because I didn't really understand what was the point in applying the limit sign, and I was really after that trying to figure out what my integration interval would be. So once I sat down and looked at the Hawks Learning Journal and understood what I was doing, it made a lot more sense. So to evaluate the integral inside the limit, we were going to use the substitution rule. So we're going to let u equal x to the 6th plus 2 and du be 6x to the 5th du. Since we have a definite integral, we must also write the limits of integration in terms of the new variable u. As I said, I had to figure out what that was. I didn't really understand. So like I said, for the lower limit of, I typed down here on my computer, for the lower limit of integration when x equals 2, it follows that u equals 2 to the 6th plus 2 equals 66. For the upper limit of integration when x equals b, it allows that u equals b 6 plus 2. So write down x equals 2 for the lower limit. And x equals b for the upper limit. So we plug those in, bring our equation down. Oops. And put the limit sign in front. B to infinity from x equals 2 to x equals b, 6x to the 5th power, x to the 6th plus 2 dx. Just put that up real quick. So I'm just looking see what I missed. Okay, so keep in mind that we have our equation x equals 6 plus 2, and yeah, we have x equals 6 plus 2. So when we plug that in, when we plug 2 in and b in, we get, for 2, we get 2, 6 plus 2 equals 66, and b, 6 plus 2 equals, Yeah, we played, and that's what we get for our equation. Sorry. So then that becomes our new. Those become substituting for our upper and lower limit. So we get. Oops. Hold on. U equals 66 on it. Integration of b6 or b to the 6th power. Put our limit sign. Make sure we change this equation. We find that we can change this equation to a derivative, or we plug in our u, so it becomes 1 over u du, which will simplify, which will in all simplify to limit b to infinity times logarithm b to 6th power plus 2 minus logarithm sine 66, which in turn will get us infinity. So with that being said, we conclude that since the integration from 2 to infinity over 6 x to the 5th divided by x to the 6th plus 2 dx diverges, we conclude that the series segment notation with an infinite number n equals 1, 6 times 6n to the 5th power divided by n to the 6th plus 2 also diverges.